So far, the problems that we've done have all been along a line. And most motion doesn't happen along a line. It curves in some way, and you have to represent it in 2 dimensions. So, like, why did we spend all this time doing stuff along a line? Well, it turns out that you can use the techniques that work along a line perfectly well in 2 dimensions. You just have to break everything up into horizontal and vertical parts. Um, so, in order to break motion into x-axis and y-axis parts, the first thing that you have to understand is related to the second common misconception in this class. And so, common misconception number 2. That is, doesn't the horizontal motion of an object affect its vertical motion and vice versa? So doesn't the horizontal motion affect the vertical motion? And vice versa. You can see how this is sort of an important question, because if we're planning to just break things up into what's happening horizontally and what's happening vertically, if those two motions affect each other, then you wouldn't be able to do this. You'd have to know what was going on horizontally and vertically all the time. And there are some cases that we're used to seeing where horizontal motion does affect vertical motion. For example, throwing a frisbee. You know that if you just drop a frisbee down to the ground, it'll hit the ground a lot sooner than if you throw it. But that is really just an air resistance effect. You spin the frisbee to help it keep its proper orientation, and then it sort of acts like a parachute in a way if it's in that preferred orientation, hovering like a disc. But the basic answer is, unless you have something in, say, the horizontal motion that affects air resistance, that affects the air action on the thing, then the answer is no. These two motions are totally independent of each other. And so I'm going to show you a video now from Mythbusters where they take a bullet and drop it from a height and fire it horizontally from the same height. And I think most people's intuition about that is that, yeah, that really fast horizontal motion of a bullet is going to keep it from hitting the ground as fast as if you just drop it. And what you're going to see is that if you do this experiment carefully, the bullet that's dropped hits the ground at exactly the same time as the bullet that's fired horizontally. Just the only difference is the one travels so far away that if you're the one shooting the bullet, you don't see it land. So let me show you that now. So that video shows us that we can just break these motions up into, depending on the direction of your x and y axes. For now, those are always x is horizontal and y is vertical. You can change those. But for now, we'll just think of x as horizontal and y vertical. So this video shows us that we can break up motions into just the stuff happening horizontally and do those calculations, and then separately do the calculations for the stuff that's happening vertically. And so in order to do that, we have to figure out how to break up position, velocity, and acceleration into horizontal and vertical parts. And in order to do that, I have to introduce the idea of vectors. And you can think of a vector, so every position, velocity, and acceleration, you can think of it as an arrow. In space. And this arrow has two properties. The first one is a magnitude. And that's the length of the arrow. And the second one is a direction. And that's I'll get rid of these. That's just the direction that the arrow is pointing. And in every case, the way we're going to break this up into x and y parts, horizontal and vertical parts, is we're going to take the arrow, put the tail of the arrow at the origin of the coordinate system. So say that's the vector that we're dealing with. Then what are called the components of the vector are the coordinates of the head of the vector. So you put the tail at the origin, find the coordinates of the head, and those are called vector components. So let's say that this has coordinates of, it's going to be a positive x coordinate, let's say 8, and the y coordinate is going to be about half as big, and it's going to be negative, so let's say that's 4. Okay, then that vector, so let's say that this vector is called u. We're always going to say that it's a vector by putting an over arrow on it like that, and we're going to represent the components of that vector as the x coordinate times this direction I. That I always means the x direction. Minus the y coordinate times j, and that j always represents the y direction. And now you have them broken up. When you're doing the x equations, you're going to use the 8. When you're doing the y equations, you're going to use the -4. So now I'm going to go through position, velocity, and acceleration this way, and then we'll get into a bunch of example problems in two-dimensional kinematics, two-dimensional constant acceleration equations. Okay, so first, position. The meaning of the arrow in position is the arrow going from the origin of the coordinate system to the object. So the position vector, and I'll write it as P with the indicator that it's a vector, is the arrow from the origin of the coordinate system to the particle. This is the one case where there's an easier way to think about it than as an arrow. In this case, just remember that, so the simpler interpretation of this is just that the components of the vector are the object's coordinates. Okay, so for example, if the object is at the location 5, -4, then simply the position vector is 5 in the x direction -4 in the j direction. And then you use the 5 for the x equations and the -4 for the y equation. For the velocity, well, we know that these vectors are always arrows with a magnitude and a direction. So the magnitude, the length of the arrow, is the object's speed at that instant. And the direction is the object's direction of motion at that instant, whatever direction the object is moving. And so to calculate this, we're going to take the arrow, put its tail at the origin, and calculate the coordinates of the head. Okay, so let's say we have, so let's do an example to calculate a velocity vector, the components of a velocity vector. So let's say that we have this object that's launched at 15 meters per second, 20 degrees above the horizontal. And we want to calculate the velocity vector components at the instant that it's launched. Well, in order to do this, draw your coordinate system. Draw that velocity vector. We know that it's 20 degrees above horizontal, and it has a magnitude of 15. And then calculate the coordinates of this point. The coordinates of that point using the trigonometry that we've done is 14.10 for x, 5.13 for y. You do that using 15 times cosine of 20 degrees for the x coordinate and 15 times sine of 20 degrees for the y coordinate. And so that says that at the instant this is launched, the velocity vector is 14.10 meters per second in the I direction. That's I means x. Don't blame me, I don't make these rules. That's what everyone else calls it, so that's what we're going to call it. And then 5.13 meters per second j, which means in the y direction. And so if you're doing, say that the first thing you're doing is using the vertical motion of this object to calculate something, then we'd be using 5.13 as the velocity at this instant, at the instant of launch. And then the last one we need is acceleration. We're going to mostly be doing free fall and projectile motion problems, but the magnitude is just the, absolute value, the magnitude of the total acceleration. The direction is the direction it's accelerating. So if you're doing projectile motion and free fall, so in free fall and projectile motion, the magnitude is going to be 9.8 meters per second squared. And the direction, if you're in free fall and projectile motion, is going to be down. And so let's see the free fall projectile motion example. Our coordinate system is this. The direction is down, so there's the arrow representing the direction. The magnitude of it is 9.8, and we're trying to calculate the coordinates of this point. Well, if you go 9.8 in the negative y direction, that gives you 0, I, 0 in the x direction, plus negative 9.8 meters per second squared in the j direction. Wait a sec, I sort of skipped a step. The coordinates at this point is what I meant to say is 0 for x, negative 9.8 for y. And so that tells us that the acceleration vector is equal to 0I plus negative 9.8 meters per second squared times j. Now, once you've broken these problems up into x and y parts, hold on a second. Little computer glitch. Okay. Once you've broken the problems up into x and y parts like this, you can do all of your problems exactly the way we've done them so far. You just do it, you either do calculations in the x direction or you do calculations in the y direction. In some problems you'll do both, a lot of problems you'll do both. But you'll always do them, in turn. You won't ever combine them. The one thing that I want you to notice though, the one thing that I think could be tricky here is that if you're trying to identify the highest point that a launched object gets to, it's only the y component of the velocity that equals 0 there. So at the highest point, only the vertical component of velocity has to be 0. So don't make the mistake of thinking, let's see, vertical component of velocity must be 0. So don't make the mistake of thinking that if you're looking for the highest point, the x component of velocity has to be 0 at that instant too. It doesn't. Okay. So let's just start going through a few examples. Come on, computer. So for the first one, let's say that an object is in projectile motion and it's launched from a height of 1 meter. And at launch, its speed is 20 meters per second. And at an angle of 30 degrees above the horizontal. And we want to calculate how far will it travel horizontally before it hits the ground. Okay, well, let me draw a picture of what's happening here. So this object is launched at this point, and it's 1 meter off the ground. And it is launched at an angle of 30 degrees above the horizontal. Okay. And because it's being accelerated down by gravity, it's going to follow a parabolic path like this until it hits the ground. And we want to calculate this distance. Okay. The first step is I'm going to figure out the components of the velocity and the acceleration. For the velocity, here's my coordinate system. And here is my vector. I know that this is 30 degrees. I know that the magnitude is 20. And I want to calculate the coordinates of this point. So if you make that right triangle, or visualize that right triangle, you can figure out that horizontal leg is 20 times the cosine of 30. The vertical leg is 20 times the sine of 30. And so the velocity at that instant is 20 times cosine of 30 is 17.32. 20 times the sine of 30 is 10. And so at the instant it's launched, which is going to be, that's when we turn our stopwatch on. So that's going to be like at V0. Our horizontal part is 17.32. Our vertical part is 10. For the acceleration, so this is for the velocity, the acceleration, that vector has to stay constant the whole time in order to use these constant acceleration equations. And here's what we know about the acceleration in free fall and projectile motion. It's straight down with a magnitude of 9.8. And so that acceleration you can represent as 0I minus 9.8 J. These are all in SI units. So the velocity is in meters per second. The acceleration is in meters per second squared. And now that we have all that stuff, we can start thinking about the calculations. So first I'm going to use the vertical components. And I'm going to use that to find the time that it takes to hit the ground. So let's figure out what we know and what we want to find from the vertical. We're looking for the time that it takes to hit the ground, because eventually, once we calculate that time, then we're going to use that time in the horizontal equations to figure out how far it travels. The acceleration, just looking at the vertical part, is negative 9.8. The position vertically when it hits the ground, we're starting, our zero height is 1 meter above the ground. You know, our zero position is 1 meter above the ground. So when it hits the ground, our position is negative 1 meter. It's 1 meter down. Our v sub 0 is the vertical part of this velocity, so that's positive 10. Now we can look for an equation that works, and we can use this one. And so this says negative 1 is equal to 10t plus 1/2 times negative 9.8 times t squared. I'll write this as 4.9 t squared minus 10t minus 1 is equal to 0. This is a quadratic equation, and so we can use the quadratic formula to find the t values, and t is equal to either negative 0.10, we know it's not that one because we don't use negative times, or 2.14 seconds. And that's the one that we want. Now that we've found that, we'll use the horizontal equation. Now we do know the time. We just figured it out. That time transfers between the horizontal and vertical. So time is equal to 2.14 seconds. The horizontal part of the acceleration is 0. So our acceleration is 0. We're trying to find the horizontal position when it hits the ground. Our v sub 0 horizontally is 17.32 meters per second. And so we'll use the same equation we used for the vertical part. This is just using the horizontal components instead. And so we get P is equal to V0t plus 1/2 AT squared. So P is equal to 17.32 times 2.14 plus, that A is 0, so this whole thing becomes 0. And we get a final answer for the horizontal position of 21.36 meters. For the next example, let's do one where we're trying to calculate the greatest height that something gets to. So let's say that we have a ball launched from a height of 6 meters with a speed of 15 meters per second. And at an angle 60 degrees above horizontal. And we want to know what's the greatest height that this reaches, or what's the highest point in the ball's flight. Okay, so what's happening here is this object is launched from 6 meters high. And it's launched at an angle of 60 degrees. Gravity is going to make its path curved like this. It's going to follow a parabolic motion. And we just want to know what's the height at its highest point. Okay, so first let's figure out at the instant it's launched what the velocity vector is. We have to use that angle and magnitude. So this is it. It has a magnitude of 15, an angle of 60 degrees. If you want to visualize this right triangle, if that makes it easier for you, you can see that the horizontal leg is going to be 15 times the cosine of 60 degrees. And the vertical leg is going to be 15 times the sine of 60 degrees. And those come out to be, so this velocity is 15 times cosine of 60 degrees is 7.5. Fifteen times sine of 60 degrees is 12.99. The acceleration is the same in all of these free fall and projectile motion problems. So I'll just write that again. That's 0 I minus 9.8 J. Okay, so now what we want to calculate is the position at the highest point. And I'm going to use the vertical part of these vectors. We don't know how long it takes, but we're not asked for that, so I'm just going to leave that off. The acceleration in the vertical direction is negative 9.8 meters per second squared. The position is what we're trying to find. That's the position when it gets to the highest point. The initial velocity, we're going to use the vertical component, and that is 12.99. And then remember that when something reaches its highest point in a projectile motion, the y component of the velocity is 0. So this is 0. And now we're looking for an equation that works with these, and we can use 2AP is equal to v squared minus v0 squared. And so that says 2 times negative 9.8 times p is equal to 0 squared minus 12.99 squared. And if you solve this equation, you're just solving for p. Well, I'll multiply it out. You get that negative 19.6 p is equal to negative 168.74. And then divide both sides by negative 19.6, and you get that the position is equal to 8.61 meters. Okay, we're almost done, but we have to think about what the question asked and interpret this in terms of, you know, where our zero position vertically is. The position at the highest point is this much above where it was launched from, this much above what we're calling our zero. And so the height is this 8.61 meters plus the height that it was launched from, which is 6 meters. And so we get a final height of 14.61 meters. For the next example, let's say that we have a ball launched at 10 meters per second, 20 degrees below horizontal, from a height of 5 meters. And we want to know how far away horizontally should someone stand to catch the ball 1 meter off the ground. Okay, so say you got somebody who has a bad back, they can't bend over, reach up too much. They want the ball to reach them when it's exactly 1 meter high, because that's the easiest place for them to catch it. How far away horizontally should they stand from this launch? To draw a picture of this, it would look something like this. You got the ground here. This ball is launched from a height of 5 meters. And it is launched at 20 degrees below horizontal, so it's launched at an angle like this. And the magnitude is 10 meters per second. And gravity is going to make this curve in a parabola like this. And this is the point where we want to catch it, where this is 1 meter. Okay, and the question is, how far apart horizontally are these two spots? Well, like always, I'm just going to start by using the magnitude and direction information for the starting velocity to come up with components. Here's our coordinate system. This has a magnitude of 10. This angle is 20 degrees. And so this would be the easiest right triangle to use. And so the x component is going to be you know, you're calculating the coordinates of this point. So you can see it's going to have a positive x and a negative y. And so the velocity for x, it would be 10 times the cosine of 20 degrees, which is 10 times the cosine of 20 degrees. I can't do that in my head. That is, oh yeah, I should be able to do that in my head actually. That's 9.4. And then the y component we know is going to be negative, and it's going to be negative 10 times the sine of 20, which is 3.42 j. And the acceleration is going to be 0 I minus 9.8 j. Okay, so what are we going to do for this one? Well, in these problems, it's pretty common that you're going to use either the vertical or the horizontal equation to find the time and then plug it into the other one. And that's what we're going to do here. That's what I did in the first example too, if you go back and look. So let's start with the vertical, because we know vertically how high this has to end. So we know something, we're going to be able to figure out our p-value for the vertical equations. We're trying to find time. The acceleration vertically is negative 9.8 meters per second squared. The p, where it's launched from is always our 0. So our position is going to be 4 meters down from that 0, which is negative 4. Our V0 vertically is what we got just right above here, so negative 3.42. We don't know V when it's caught, and so we'll look for an equation that'll let us solve for T, and the one that works. In these ones where you're going to find a T using one dimension and then plug it into the other dimension, you're very often, maybe almost always, going to use this equation. So we have negative 4 is equal to negative 3.42 t plus 1/2 times negative 9.8 times t squared. And if I rearrange that, I can do it as 4.9 t squared plus 3.42 t minus 4 is equal to 0. That's a quadratic equation, so use the quadratic formula and you get that t is either negative 1.32, which we know it can't be because we are not using negative times, or positive 0.62 seconds, and that's the one that we want. Now that we have the elapsed time, we can plug this into the horizontal equations. So we know t is equal to 0.62. A, this is the horizontal one, so A is equal to 0. We're trying to find P. Our V0 is the horizontal component of the velocity when it's launched, so 9.4 meters per second. And we'll use this equation again. P is equal to V0t plus 1/2 AT squared. So P is equal to 9.40 times 0.62 plus 0. This term goes away because A is 0. And we get that P is equal to 5.83 meters. So if the person catching this ball stands horizontally away 5.83 meters, they'll catch this ball at exactly a height of 1 meter off the ground. For the last example, let's say that a ball is launched horizontally at 25 meters per second from a height of 3.5 meters, so 3.5 meters high. And then the ball is caught 20 horizontal meters away. So first, let's calculate what's the height the ball is caught at. And second, let's calculate the velocity vector of the ball right before it's caught. I don't know why I put an exclamation point there. It's really not that exciting. Okay, so what does this look like? This ball is launched horizontally, so that's its starting velocity, at a speed of 25 meters per second. This height is 3.5 meters. And gravity is going to make it follow a parabolic path. And we want to calculate this height, given that this is 20 meters. And then for part B, we want to calculate the velocity vector. Well, that velocity vector at the instant that it's caught is tangent to the path. So it's going to be something like this. And if you think of putting the tail of this vector at the origin of a coordinate system and calculate the coordinates of the head, we know we're going to get this velocity vector having a positive x component and a negative y component. Okay, so for part A, this time, I think it's probably more common that in order to calculate the time of flight, you first use the vertical problem and calculate the time and then plug it into the horizontal. But in this case, what we know is actually a horizontal distance. And then, so we're going to start with horizontal, find the time from that, and then plug that into the vertical equations. So I'll start with the horizontal. Oh, one thing I didn't do was draw the, on all these other examples, I've started by drawing the coordinate system with the starting velocity vector to calculate the components. In this case, it's pretty simple because it's horizontal. It's only going along the x-axis. And so if you did that, you would just get 25 for the x component and 0 for the y component. You know, think of that as it would be coordinates, the coordinates of the head would be 25, 0. Okay, we're looking for the time. We know that the acceleration, since we're doing horizontal, is 0. The position horizontally, we know, is positive 20 meters. The horizontal starting velocity is 25 meters per second. And so I'm going to use the equation P is equal to V sub 0 t plus 1/2 AT squared. So 20 is equal to 25t plus, since a is equal to 0, this is 0. And so t is equal to so t is equal to 4/5, so 0.8. And now that we have that, we can plug this into the vertical problem. We know now that the time when it's caught is 0.80. The acceleration, now that this is vertical, is negative 9.8. The position, if you look up at this problem, actually we're trying to calculate the height that it's caught. So I'm going to put this over here. And then V sub 0 for the vertical part is 0. And we'll use P is equal to V0 times T plus 1/2 AT squared. So P is equal to 0 plus, plug this stuff in, you get negative 4.9 times 0.80 squared. And the answer that you get is that P is equal to 3.14 meters. Well, that's not quite the answer we're looking for. We're looking for the height that it's caught. This is negative. So what height is it caught at? Well, 3.5 meters high is our 0. And so our height is going to be 3.5 minus 3.14, which is 0.36 meters. So 36 centimeters off the ground is where this is going to be caught. Okay, now the last thing that we want to calculate here is the velocity vector, the components of the velocity vector. Well, we know we're looking for the velocity vector at the time that it's caught, and we already have that elapsed time. So I just have to calculate a horizontal and a vertical component of the velocity. I'll start with horizontal. It doesn't matter which one you do first in this case. Our t is equal to 0.80 seconds. Our A for horizontal is 0. This is the stuff that we know. Our V sub 0 horizontally is 25 meters per second. And we're trying to calculate V at time 0.8 seconds. The equation we're going to use here is V is equal to V0 plus AT. Since A is 0, this just comes out to be 25 plus 0. So V is equal to 25 meters per second. And it turns out that that's something you that always ends up being true. For the horizontal component, the velocity never changes in free fall and projectile motion because the acceleration in the x direction is 0. And now vertically, we know that the time is 0.8. This time we know the acceleration is negative 9.8. Okay, negative 9.8. Our V sub 0 is 0, and we're trying to find V. We'll use the same equation again. V is equal to V0 plus AT. And so V is equal to 0 minus 9.8 times 0.8 and so V is equal to negative 7.84 meters per second. And if you put these two things together, you get that at the instant this ball is caught, V is equal to 25 times I minus 7.84 J. And the units are meters per second. You could put that in there too. You probably should. So you could write it as like 25 meters per second I minus 7.84 meters per second J. Come on. Okay. All right, so there it is. And if you think of this as the coordinates of the head of the vector when the tail is at the origin, you can see that the signs of those match with what I drew for this red vector. We knew it was going to have a positive x component and a negative y component.